Hello and welcome in EMWorks2D for SOLIDWORKS. In this particular example, I will go over how the 2000 Prius motor is simulated inside EMWorks2D for SOLIDWORKS. Before I begin, let me briefly describe our model here. We have a 2D geometry of a PMSM equipped with 48 slots and 8 V-shaped rotor poles. Its single-layer windings are made of 3 phases. So, in our motor geometry, we have the rotor subassembly consisting of the rotor core, the shaft, and interior PMs, which will be rotating with a certain velocity. We also have the stator subassembly consisting of the stator core and coils, as well as the band part englobing all the rotatory parts of our model, and the outer air parts englobing the entire geometry. The electric motor, equipped with both PMs and coils, will be rotating under no load thanks to the magnets and according to Maxwell's law. Therefore, it will produce the so-called cogging torque. However, once the coils are excited, the total load torque will be equal to the sum of the reluctance torque and the torque produced by the magnets. Let us see how we can use EMWorks2D to understand the magnetization direction of the PMs. Next, we will see how to set up the simulation inside EMWorks2D for SOLIDWORKS. EMWorks2D is an add-in product to SOLIDWORKS. So once you design your model geometry inside SOLIDWORKS, you can do the electromagnetic simulation right inside of it. EMWorks2D studies are organized inside the EMWorks2D Manager tab, and each study is organized as a separate study. For example, we are going to do a no-load study with coil loss of the Prius motor. To do a transient magnetic study, we can just create a study. Each study has a particular name. We also need to check compute circuit parameters to get the resistance, inductance, and also flux linkage results. For each transient magnetic study, you need to specify the time duration, means the start, end, and step time. This study is coupled to rotational motion. Now, when you couple to rotational motion, you first have to specify the rotation velocity. Then, you select the global rotor angle variable defined in SOLIDWORKS. You select the moving components, in this case, the rotor subassembly, and also the band. Once you define the study, it's now time to define the materials and proceed with the next simulation setup. Next, we will look at defining materials for the various geometry components. EMWorks2D has a large material library with different categories that are widely used in the industry. The material library is also customizable, which means that the users can also define their own materials with their properties and use them for their simulations. Here are the permanent magnets. I'll be using a customizable material. Now when you do edit material, you get to see the coercivity and also remnants of the magnet material. You also have the magnetization direction, which can be easily defined by specifying the coercivity direction of the magnets using the local coordinate systems. In this case, all the magnets are rectangular shaped. Their directions are locally defined using the local coordinate systems initially defined in the SOLIDWORKS design tree. Next, the stator and rotor cores are made of M19 material defined from the material library. This material is characterized by coil loss properties. We can edit the material and view here the stacking factor and also the coefficient of the coil loss function, namely the hysteresis, eddy, and also excess coefficients. The coils are made of conductor material. in our case, the copper from the conductor material folder in the material library. We also have the air geometry indispensable to any simulation because the magnetic field will be located in this region, and you can also assign the air material to it. The band and the shaft parts are also defined as air. The windings are defined in this section with a null excitation. We have here 3 windings: phase A, phase B, and also phase C, and each have outer and inner coils. We can, for example, edit the phase A winding to check its properties. Each winding has a name, and you can specify if it's current or voltage fed. The current source type and properties are then defined in this table. We can also edit the A+ coils to check their properties. You can see for the A+ coils that the faces are selected, and also the properties including the wire diameter and the number of turns. For the A- coils, we can see that the current direction is reversed. In the same way, we can define the rest of the coils for the 2 remaining windings, with the selection of the adequate faces. The torque is defined through the virtual work by selecting the moving faces for which you want to compute the torque. Now, let us look at the simulation results. We will first look at the cogging torque results. Since it's a transient magnetic study, all results are defined in the results table according to the varying time. Still, we can plot the cogging torque versus the rotor angle using the 2D plots option. Here, we can observe 12 periods of the cogging torque with an approximate average value of 0 Nm and a maximum value of almost 2 Nm. Now, all values are easily listed in a tabular format, which can be exported in a format of your choice, namely TXT file or Excel file. We can also plot the induced voltage versus time. Here, we can observe one period of the 3-phased induced voltage, which are shifted in time. The curve shows harmonics in the back EMF, making it with a non-sinusoidal shape. Now, let us take a look at the no-load flux linkage and plot it versus time. Here, we also observe one period of the 3 shifted curves having a fixed magnitude of 0.14 Weber. Next, we will look at some quantitative plots in EMWorks2D. For example, we can take a look at the magnetic flux density mapping. One can observe that the stator teeth has higher magnetic flux density once they are entirely facing the magnets. Now, I'll go over how to use the previously defined no-load study and then add a sinusoidal excitation to simulate the on-load performance of the Prius motor. This will save the time of redefining the simulation input parameters. Now, I'll just drag the no-load study, then drop it to create an editable version of it. The next step consists in changing the study name, so I will change it to onload. Since all parameters are already defined, I'll show you how to edit the excitation of the stator windings and define it as a sinusoidal one. Let us first check the windings excitation in the case of current-fed coils. As seen previously, the single-layer winding is made of 3 phases. I'll edit the phase A winding. We can see here that the coil type is set to current-fed coils. In the Current Source tab, the current source is defined as sinusoidal. The current source parameters are then defined. They include the damping factor, the frequency, the current amplitude, the current offset, as well as the pulse delay time. One can notice that the phase A winding has a delay time, and for the remaining phases, we also have to add the 120-degree shift expressed in seconds. So, if you consider that one period is equal to 2 pi, then 120-degree shift is equal to 1 period divided by 3. Now, we can look at the simulation results. Let us first check the sinusoidal input current versus time curve. It includes the phase A, B, and C, and clearly shows the shift of phase A with respect to the origin of time. Also, the shift of phase B and C with respect to phase A. We can also take a look at the onload torque versus the time curve. The onload torque versus time curve shows a maximum value of 369.6 Nm and an average value of 320 Nm approximately. Next, we will check the magnetic flux density obtained at onload conditions. From this plot, one can note a maximum flux density at the edges of the rotor poles. EMWorks2D has a very powerful visualization capabilities that can help you to understand the behavior of the magnetic field inside your motor geometry. And also, you can get a sense of all the numerical values of the motor performance. Thank you very much for watching this video. Now for more information, please do not hesitate to visit our website.